Okay, so hello and good morning, everyone. Welcome to ICT experiment number 6. So today's experiment is about study of novel devices and comparing them with single gate MOSFET. And the aim of the experiment is to obtain the different characteristics, like for example, the transfer characteristics, the output characteristics of a single gate MOSFET, double gate MOSFET, silicon nanowire MOSFET, carbon nanotube MOSFET using the simulation tool FET Toy from nanohub.org, and then compare these four technologies using the following characteristics: the drain current versus the gate voltage relation, drain current versus drain voltage relation, mobile charge versus the gate voltage relation, and quantum capacitance versus the gate voltage relation. So let us directly start now. So we will follow the stepwise procedure, and we will go on to have a complete overview of the four cases in this experiment. So first of all, we have to go to nanohub.org and log in with your somaya.edu email ID. So let me do that. Yeah. So I've already taken care of it. I've already logged in via the Somaya email ID. And now we have to go to resources. And from there, we have to select FET toy. So over here, we have the tools. From here, you scroll down and search for FET toy. It will be arranged alphabetically. So we'll search for FET toy. Yeah, FET toy, click on it. And next, click on launch tool. So basically, this FET toy tool will calculate the ballistic IV characteristics for a conventional single gate MOSFET, double gate MOSFET, nanowire MOSFET, and carbon nanotube MOSFET. We can click on this learn more to view about more details. So let's click on launch tool. So once you click on this launch tool, GUI interface will appear, right? And here the description is also written. So let us understand what all things it contains. Okay, so let us begin. So from here, we have to select the following devices one by one. Let me make this font size as 100. Yeah. So we need to select the following devices. Just for example, from here, we can select the various MOSFETs using the different technologies: single gate MOSFET, double gate MOSFET, silicon nanowire, and carbon nanotube MOSFET. Fine. And we have to vary the parameters of each of them for four cases given below. And we have to note down the readings from the each characteristics. Okay. So there are some various parameter specifications which are given for each device, which will keep it as it is. So this is my gate insulator thickness for a single gate MOSFET. Let me just maximize and view it for your reference. Yeah. So this is your gate oxide thickness, right? You know what is gate oxide thickness? It is given in nanometer. Then next we have is gate insulator dielectric constant. Keep it as it is by default. Then we have the effective mass ratio, okay, which is around 0.19. And then we have the valence degeneracy. It's basically for the carriers confined in the channel region, okay. And for silicon, it's normally 2. Then we have floating boundary flag, keep it no only. And then we have the body thickness. This is the active region, that is body thickness. So yeah. And next we have is source doping. So it is 1 into 10 raised to 20. So keep it as it is per centimeter cube. Fine. So here is the small description of your single gate MOSFET. We have a source and a drain, and then we have a silicon dioxide, and followed by the gate, right? So let us begin with the next description of the model. So this model parameters, we have to keep it as it is. Threshold voltage, you keep it as it is as 0.32. Gate channel control parameter, drain channel control parameter, also keep it by default. Series resistance, also keep it by default, right? We'll come back to it. What is this gate control parameter? So basically, if you keep this, description will come automatically. So basically, the gate control parameter is the gate capacitance divided by the sum of the gate, source, and drain capacitance. Okay. Basically, it will control the sub-threshold swing, right? According to that formula, S is equal to 2.3 kT by Q divided by alpha G. So when alpha G is equal to 1 and alpha D is equal to 0, there is a complete gate control and the subthreshold swing is ideal. And DIBL, that is the drain induced barrier lowering, is 0. Okay. So here you can enter a number between 0 to 1. And then we have drain control parameter, which is alpha D. It is the drain capacitance divided by the sum of gate, source, and drain capacitances. It controls the drain induced barrier lowering, Dibble. According to the Dibble, it is given by S into alpha D divided by 2.3 kT, 2.3 kT by Q, where S is the subthreshold swing. Okay, so this also number we keep it as it is. And next we go to environment. So in the environment, we have the ambient temperature 300 degree Kelvin, that is 27 degrees Celsius. Gate voltage, initial and final values given, and the gate voltage bias points are given, right? So we can change the settings. So yeah, so let us begin what we have to do in the first part. So all these parameters will be there for the different MOSFET. For single gate MOSFET, these are the parameters. For double gate MOSFET, we will view right now. Yeah, here it is. So for a single gate and double gate, the parameters are the same. The model parameters are same. For silicon nanowire MOSFET, the parameters are different slightly. So here we have your nanometer diameter, then the gate insulator thickness, gate insulator dielectric constant. Then we have your transport carrier transport effective mass. Then we have the valence degeneracy. Okay. And then also for the carbon nanotube, the parameters over here are different. We have the nanotube diameter, gate insulator thickness, and gate insulator dielectric constant, right? So these are the various device model parameters. And now we go to the single gate MOSFET and let us start with a simulation. So over here, these parameters are given, right? So there are 4 cases. So let us see them one by one. What we have to do in case number 1 and 2 and 3 and 4. So for the first case, we have to observe the characteristics of drain current versus gate voltage characteristics. So for the 4 devices, that is single gate MOSFET, double gate MOSFET, silicon nanowire MOSFET, and carbon nanotube MOSFET, we have to carry out the simulation. So first we have to note down the value of the drain current, which will be in microampere per micrometer. For single gate MOSFET and double gate MOSFET, we have to note down the value at Vg equal to 1 volt, Vg equal to 1.5 volt, and Vg equal to 2 volt. Okay, so and this has to be carried out at drain voltage equal to 2 volt. So let us start. So first of all, we have to go to the environment, and initial gate voltage, we have to give it around 2 volt. Now, why 2 volt? Because over here, maximum reading is 2 volt. Okay, the reading we have to take it as 2 volt. And also the drain voltage has to be varied between 0 to 2 volt only. So here we enter 2 volt. And number of gate bias points, basically this will decide the resolution. So this we will keep it 40. Here also we will keep it 40. Fine with it. And now we are ready to simulate. So we'll go to the device and click on simulate. Okay, so here you got the result of drain current versus the gate voltage. Basically, this is my transfer characteristics. So you will say ki this doesn't look like a transfer characteristics. Yes, correct. Reason being is that the drain current is plotted in logarithmic plot. If I bring it back to the linear plot, here it will be a familiar transfer characteristics, right? Your drain current versus your gate voltage. So you can go over here and remove this second part, which is the drain current at that particular value. So you can untick it. So you will get only one screen now. Okay. So let me let me show you how to take the reading now over here. So we have to take the value of ID at Vg equal to 1 volt, right? Already Vd is 2 volt. So you can bring your cursor over here around 1 volt. So you can take it approximately equal to, here you can expand it and approximately, I'm just saying it is around 1 volt. So you can write it as 1.02. So the value of the current over here at 1.02 is my gate voltage. At drain voltage equal to 2 volt. The value of the current is coming out to be 2900 microampere per micrometer. Okay, so this is how you can take the reading, or you can expand this section and take the reading exactly at 1. Or what you can do is you can write this this reading of VG as 1.02 in the write-up itself. So here in the write-up itself, you will write 1.02 volt. That will also suffice. Okay. Or else you can increase the number of data points from 40 to 60. Maximum you can give it 60. Okay. Accordingly, so that you get the reading at 1 volt. Fine. Now, similarly, you have to carry out the reading at 1.5. So around 1.5 volt, it is 6,000. 150, and last reading you have to take it as 2, right? So when it is at 2, you can take the print screen. Okay, when you take the print screen, also the current is noted down, 9710 microampere per micrometer. So this reading you have to note down in your observation table at 2 volt. Okay, so this is how we have to conduct the take the readings for single gate MOSFET. Now exactly same way you have to do it for double gate MOSFET. But before going there, let me tell you something about the logarithmic plot. It gives you very important information, right? What information does it give you? Now you see this curve, it's not starting from 0. So basically, this is the logarithmic plot. We have a log of ID. Your drain current is logarithmic, and your x-axis is your normal axis. That is the gate voltage. So what information does it give you? If you see this point over here, when the current, the current is starting, this current which you see over here, 0.026 microampere per micrometer, is my off state current. Okay, my ID off, that is your off state current of your MOSFET. It is not 0 actually, right? Because of the sub threshold current, it is not 0. And this is very, very important. Your I off current is determined for the device, and your ion current is basically the highest value over here, which is coming same as 9710 microampere per micrometer. So this is also a very informative plot, which will give you information about the off current of your MOSFET. Okay, so off current of your MOSFET in this case is, even if the gate current is 0, is given by 0.026 microampere per micrometer. Now, if you go to the linear plot again, this information might not be available. You might see over here that the gate drain current is 0, but in reality it is not 0. As you can see, if I place my pointer over here, it is 0.026 microampere per micrometer. But since it is starting from 0, it will look like it is 0, but it is not. So that information can be captured more thoroughly in the logarithmic plot. So that's why we plot the logarithmic plot. Okay, so yeah, so you have to take the reading like this. Now we have to go to the double gate MOSFET and again simulate it. So we have to remove this, let's say. So what you need to do is you need to take the reading for the linear plot. You can plot either one. You can plot the logarithmic plot or the linear one. Anyone will do. Okay. The linear one already you're familiar with. Logarithmic plot you might be seeing for the first time. So here we have to take it for any one case, let's say at 2, and take the print screen of this. Okay. Now similarly, you have to do this for your double gate MOSFET. So I'll click on the double gate, simulate it again, and you will soon get the plot of drain current versus your gate voltage. So again, you have to note down the reading at VG equal to 1 volt, VG equal to 1.5, and VG equal to 2 volt for a double gate MOSFET. So here is the plot again came. It is again a logarithmic plot by default. So you can remove this dotted line, and then you can again take the reading at 0. You see it's almost same, and at the highest point also it's around 21500 microampere per micrometer. So what you can do is you can go to this linear, and now you can take the reading at VG equal to 1 volt, at VG equal to 1.5, and at VG equal to 2 volt. What's the current value, and note down that in your observation table. Okay, so this is about the first table. Now let's move on to the silicon nanowire MOSFET. Again, we have to take it at 1 volt, VG equal to 1, VG equal to 1.5, and VG equal to 2 volt. So let us do that. So we'll select over here the silicon nanowire MOSFET. So for silicon nanowire MOSFET, the parameters are slightly different. We have already discussed them. Now again, we click on simulate. So again, by default, it is giving the current in microampere. This is the axis. If we clear all, and then simulate it again, it will be much better. Yeah. So this is the micro, drain current in microamperes. So again, we will remove the, the drain voltage for the dotted line. And now we can check. So you can see this is my off current. So off current in a silicon nanowire MOSFET is very, very small, 0.0000256 microamperes. Okay, so the off current for a silicon nanowire MOSFET is very less. And the on state current is given over here at Vg equal to 2 volt. It is 86.2 microamperes. Okay, so either you can take the reading for a logarithmic plot or you can take it for the linear plot. Anyone will do. Okay, so this linear plot you are familiar with, right? So you can take the reading at Vg equal to 1 volt, Vg equal to 1.5, and Vg equal to 2 volt. Fine. Now similarly, we have to select a carbon nanotube MOSFET, and again simulate it and note down the parameter. I mean, note down the drain current for Vg equal to 1 volt, Vg equal to 1.5 volt, and Vg equal to 2 volt reading. Okay, so the simulation is still running for carbon nanotube. So it will take around 10 to 15 seconds to complete the simulation and give you the plot. Okay, so now in few seconds it will come very shortly. Yeah, so it has already come up, right? By default it is in the logarithmic plot. Again, I will remove the dotted line drain voltage. Yeah, so now you see in case of a carbon nanotube MOSFET, the off state current is around 0.000256 microamperes. It's very less compared to the conventional single gate and double gate MOSFET, right? So again, you can, this is the logarithmic plot. You can go to the linear scale and have the, the print screen of this at 1 volt, at 1.5 volt gate voltage, and at 2 volt. Okay, so this way you will complete the case number 1. Case number 1 was drain current versus the gate voltage characteristics. So all the values you can enter it. And note that for every MOSFET type of the device, that is single gate, double gate, silicon nanowire, and carbon nanotube, you have to take the print screen. So total 4 print screens will be required at any one value. Let's say at Vg equal to 2 volt, you have taken it, right? So this way we have to conduct the experiment and keep this on. I mean, keep it there at 2 volt. What is the drain? I mean, what is the drain current? So this print screen we have to take, okay, wherein the value of drain current is visible. So at 2 volt, you can take it. I mean, right now it is right. So right now this print screen you can take for your particular case. Okay. Now let's move on to case now. This was about the case number 1. Let's move on to case number 2. So case number 2 is fairly simple. We have to repeat, for the the simulation for all the 4 types of devices. Right now we are plotting drain current versus the drain voltage, that is the output characteristics at Vg equal to 2 volt. So we have to note down the value of drain current, that will be in microampere per micrometer for silicon gate MOSFET and double gate MOSFET, right? And for the silicon nanowire MOSFET and carbon nanotube MOSFET, the current will be in microamperes. So here we have to take for drain voltage equal to 1 volt, drain voltage equal to 1.5 volt, and drain voltage equal to 2 volt. Okay, keeping gate voltage as 2 volt constant. So let us do that. So for this, we have to go to the environment, and here we have to keep the number of bias points for gate as 5. Okay, I will tell you the reason why 5 later on, but right now you have to take it as 5. So again, go to devices. So yeah, right now the carbon nanotube MOSFET is there. So let us simulate it, no problem. Let us clear all and let us simulate this, no problem for it. So we are taking over here carbon nanotube MOSFET. We are measuring the drain current value and noting it down for Vd equal to 1 volt, ID value for Vd equal to 1.5 volt, and ID value for Vd equal to 2 volt. So let us see. Yeah, we are getting the graph. Now we have to select the drain current versus the drain voltage graph. Okay, so you remember we have taken the number of gate, number environmental parameters. Over here, we have taken number of gate bias points as 5. If you would have taken 40, then you would have got 40 graphs over here. That's why we have taken it as 5 for the second case. Okay, so right now what we have to do is we have to measure the current value the current value at VD equal to 1 volt. So yeah, at VD equal to 1 volt over here, somewhere close to it. This is for gate voltage 0.5. This is for gate voltage 1 volt. This is for gate voltage 1.5. The last one is for gate voltage 2 volt. So you have to take this reading at 1, at VD equal to 1 volt, at VD equal to 1.5, and at VD equal to 2 volt. Okay, so and this print screen we have to take, right? So very simple it is, no complexities involved over here. Then you have to repeat the same. This is, as you can see, this is my output characteristics of a MOSFET. Now this is for a carbon nanotube MOSFET. Let's go to silicon nanowire. So silicon nanowire, and again go to simulate. Don't change anything else. Keep all the parameters by default. Okay, so it will take some time. So for that time, we can describe this. So silicon nanowire MOSFET ID value at VD equal to 1 volt, ID value at VD equal to 1.5 volt, and ID value at VD equal to 2 volt we have to take. Okay, so we have got the graph. So we have to select the second option for the output characteristics, which is the drain current versus the drain voltage. And at VG equal to 1 volt, so here it is, gate voltage is 2, and at VD equal to, you can select it near to 1 volt. Okay, whatever the value you are getting over here, you can enter that value into observation table. That is, gate voltage, drain voltage is 1.02 volt, and that particular value, my current is 83.3 microampere. So this way we have to take it at 1, drain voltage equal to 1.5 volt, and drain voltage equal to 2 volt. Okay, so at 2 volt you can take the print screen. The current will be visible, and the gate voltage also will be visible. So this way you can complete it for silicon nanowire MOSFET, and similarly you can complete it for silicon gate MOSFET and double gate MOSFET. But for silicon gate MOSFET and double gate MOSFET, let me show it to you once. Let me clear all and simulate. The current will be in microampere per micrometer. So only that is the change. The rest, all the things remains the same. Okay, the current over here will be in microampere per micrometer. So again, you have to take it at VD equal to 1, at 1.5, and at 2 volt value. Yeah. So here is the graph we got. Now let me go to the drain current versus drain voltage. Here it is, right? So here you have to take it at 1 volt, at 1.5 volt, and again at 2 volt. And again, take the print screen for 2 volt. Okay, so you have to note down this current value. Fine. So let me clear all now, and let me go. This was about the case number 2. That is the output characteristics, drain current versus the drain voltage characteristics. Okay, but one more thing we have to do is over here, for this characteristics for VG equal to 2 volt, we have to measure the value of RO. Now RO is the output impedance of the characteristics, right? So what you need to do is, we have to consider RO is what? Delta VD upon delta ID, right? So you can consider any of the two readings. Let's say you can consider at VD equal to 2 volt and VD equal to 1 volt. So that what is delta VD over here? 2 minus 1, that is 1 volt, divided by the current levels. So what is the current at ID equal to, what is the current at 2 volt? Subtract the current at 1 volt. Okay. So what you will do is, let me just, yeah. So RO will be equal to, let me just try and writing it down over here, text form mein. So RO will be equal to VD2 minus VD1 divided by ID2 minus, oh sorry, we can write ID2 minus ID1. Okay. So what is this ID1 and ID2? Basically, RO will be, delta ID upon delta, delta VD upon delta ID, right? So here also your bracket will come. Okay. So how will you measure this RO value? So here your reading you will get, right? So here one reading you will get. Let's say this reading, its value is, let's say its value is ID2. Okay. So over here, correct? And now this reading value is ID1. Let me write ID1. Let me adjust it properly. Okay. So, and this is your VD1. VD1 is 2 volt. VD2 is 2 volt. VD1 is 1 volt. And your ID2 value, whatever you get over here, and ID1 value, whatever you get over here, right? From the graph. So if you do that VD2 minus VD1 upon ID2 minus ID1, that will give you RO, which will be in kilo ohms. Okay, it will be a large value in kilo ohms. So you have to note it down. I hope that this is clear. And similarly, you have to do the same thing for carbon nanotube MOSFET. Okay, so from the readings, you can determine the value of your output resistance RO. Fine. Now let me clear all the drawings. Okay, fine. So let's proceed forward for the third case. So for the third case, it's fairly simple. We have to determine mobile charge versus mobile charge density versus your gate voltage, correct? So here the mobile charge divided by centimeter square. You have to note down for a single gate MOSFET at VG equal to 1 volt and at VG equal to 1.5. And similarly over here for the silicon nanowire MOSFET and carbon nanotube MOSFET also you have to do the same thing. So here it will be a mobile charge density divided by centimeter per centimeter. Okay. Again, you have to take it at VG equal to 1 volt and VG equal to 1.5 volt. So what changes we have to make over here is go to environment and VG, since we have to take it at 1.5, so you can take it as 1.5 volt maximum. So here I'm putting 1.5 volt. Okay. And here the number of points can be increased now. So let's say, yeah, at VG equal to 1 and 1.5, right? So let's say I can give it around 30. Okay, fine. And the drain voltage, you can keep it as it is. The number of points will be as it is because it is for 2 volt. Okay, so let me go to the devices. And here we have single gate MOSFET. Let me simulate it. It will take couple of seconds to simulate and give the plot. We have to select mobile charge, density per centimeter cube. For that value, you have to note down the value at VG equal to 1 volt and VG equal to 1.5 volt. So let us try to do that. Let me see if the graph has come. Yeah, it has come. So now you have to select from here mobile charge versus mobile charge divided by Q versus the gate voltage, because that is the experiment, right? Mobile charge versus the gate voltage. Yes. So you have to note it down at VG equal to 1 volt and VG equal to 1.5 volt. Okay. So yeah, we can remove the dotted one from here. And here also, this is the logarithmic plot, right? So at we can give it to linear plot. And here you can determine the mobile charge at VG equal to 1 volt. Okay, at VG equal to 1 volt. Basically, this you can take it at logarithmic plot or your linear plot. Anyone will do. So yeah, so because both are means the same, only the range is different. So here the mobile charge, your mobile charges per divided by Q, mobile charge per Q divided by per centimeter square will be actually how much? 1.32. Okay, at 0 volt, at gate voltage of 0 volt. And then you have to take it at gate voltage of 1 volt over here like this, at 1 volt, nearby 1 volt, and similarly at around 2 volt. Okay, so either this is the value of your mobile charge density, 1.45 e raised to 13 per centimeter square. Okay, so this is the value we are getting it. Fine, at 1.5 volt gate voltage. So this is, you have to do it for double gate MOSFET. We have to also do it for your silicon nanowire. Let me show it for silicon nanowire once. So let me simulate it again. So this value you have to write it over here. Okay, this will be per centimeter square per centimeter square. That is absolutely correct. And this for the characteristics with VD equal to 2 volt for devices at silicon nanowire and carbon nanotube. Again, you have to repeat the same procedure. So here we have to select for mobile charge divided by Q versus gate voltage. Again, remove the dotted line from here. This is logarithmic plot. You can go for logarithmic also and note down the charge density over here. That is 5.61 like this into 10 raised to 6 per centimeter. And here also at 2 volt. So complete this for silicon nanowire as well as for your carbon nanotube MOSFET. Okay. So these all readings will comprise of case number 3. So you can enter the readings over here. Let us go to the last part now. Last part is quantum capacitance versus the gate voltage. So quantum capacitance for silicon nanowire MOSFET, carbon nanotube MOSFET, single gate MOSFET, and double gate MOSFET. We have to take the reading. Okay. So the unit for the quantum capacitance for single gate MOSFET and double gate MOSFET will be farad per centimeter square. And for a silicon nanowire and carbon nanotube MOSFET will be farad per centimeter. Okay. So note down this value of quantum capacitance at Vg equal to 1 volt and Vg equal to 1.5 volt. So let us do that. So right now I will select silicon nanowire. It's already selected. From here, first of all, let me clear all the plots again. So let me simulate it for silicon nanowire first. Since we are in the silicon nanowire MOSFET, we will already the devices selected. So quantum capacitance, click on quantum capacitance versus gate voltage. Yeah. So here again, I will go over here and deactivate the dotted line. And here you have to note down the quantum capacitance value at Vg equal to 1 volt approximately. So for a higher resolution, what you can do is you can increase the number of data points over here, make it 60. So you can make it 60 and then accordingly note down the readings at Vg equal to 1 volt and then at Vg equal to 2 volt. At Vg equal to 2 volt, you can take down the print screen. So right now it is 2.02 into 10 raised to minus 12 farad per centimeter. So that reading, we have to write it over here. Okay. And similarly, you have to carry out the procedure for carbon nanotube MOSFET also. So let me click on it and click on simulate. So it will give the plot in few seconds. For carbon nanotube MOSFET also, we have to note down the value of quantum capacitance at Vg equal to 1 volt and Vg equal to 1.5 volt. So let me see, it's taking some time to simulate. It will come very soon. No problem. So keep all the parameters by default. Okay, so let me go to quantum capacitance versus gate voltage, deactivate the dotted line over here and note down the reading at Vg equal to 1 volt, right? And at Vg equal to 1.5 volt. So these readings we have to enter in the table. Okay. And similarly, we have to do it for single gate MOSFET. Let me show you for single gate MOSFET once, and then we will wind up this session. Okay. So let me simulate for single gate MOSFET. Rest all the parameters as it is. Now we will select quantum capacitance, gate voltage versus gate voltage. We'll deactivate the drain voltage from here. And here we have to take it at Vg equal to 1 volt, the value of the quantum capacitance, farad per centimeter square, and Vg equal to 1.5 volt. At 1.5, you can take the print screen. And similarly, we have to carry out the procedure for your double gate MOSFET. Okay. In this way, you will complete the reading for case number 4. Fine. So this way you will complete the entire table for all the 4 devices. Then we have to upload, you have to upload total 4 types of plot for each devices, right? So total 16 plots will be there. Okay, along with the observation table and post lab questions, etc. So these are your post lab questions, right? So for all the 4 cases, you write the unique conclusion. Okay, so try to attempt this post lab questions on your own and and write the conclusion for each case. So in this way you can carry out the simulation for the novel devices. For example, for 4 devices, that is single gate MOSFET, double gate MOSFET, silicon nanowire MOSFET, and carbon nanotube MOSFET. For the 4 cases, that is case 1 was drain current versus gate voltage characteristics, case 2 was drain current versus drain voltage characteristics, case 3 was mobile charge versus your gate voltage, and case 4 was quantum capacitance versus your gate voltage. So kindly complete this experiment and the simulations in nanohub.org on time. So that will be all for this session. Kindly complete your work on time. So yeah, thank you for joining.